So let's start. Estimator theory explained via regression. First, let us introduce to regression. So regression is a supervised learning method. We have a training set with n points, xi and yi. Xi are values at which we want to evaluate or predict a function, and yi are labels, the function values that we want to predict. Xi is a vector. Yi in general could be a vector, but in this case we will assume that it is just a scalar. Now the aim is that we want to approximate the function f that takes x to y. So in other words, we assume that the data pairs x and y have been generated by a function that has been observed, and perhaps there was some noise in the measurement process, but there is this underlying function that generates the data, and we want to estimate the function as good as possible. So in order to do this, we parameterize f by a family of functions, y hat, and y hat is our predictor. We call y hat I the prediction of our model or predictor at data point number I. So that is the function y hat evaluated at xi. And additionally, the function will depend on a set of parameters w. Those parameters we have to find. This is the learning problem, to find the parameters w such that the model y hat predicts the function f as good as possible. So we can say the learning problem is to find w such that we minimize the errors of the prediction, so the residuals delta, and every delta I is the difference between the label yi that we have for training and the prediction at the point xi with the current parameters w. Let us look at a visual representation of a simple linear regression. So suppose we have measured the blue data points at positions x1 through x4. We have measured y1 through y4, and we assume that this data has been generated by a linear model. So we fit a line by estimating parameters, and our predicted line, which has the form y hat of x equals w1 plus w2 times x, gives rise to the predictions y hat 1 through y hat 4, the red points, at the positions of the data x1 to x4. The differences delta 1 through delta 4 are the residuals between the prediction and the labels. Those we want to minimize by varying the parameters w. In order to specify the learning problem, we have to say how exactly do we want to measure the differences delta. So how do we want to measure these residuals? And since the residuals in general are a vector, we have to define a vector norm. So a common way to do this is to use the so-called p-norm. So the p-norm of a vector is simply the pth root of the sum over the entries taken to the pth power. The most common choice is p equals 2. That is least squares regression, and goes back to Gauss. In least squares regression, we simply minimize the sum of the squared differences between prediction and labels. We have removed here or ignored the square root because we are minimizing, and the square root is a monotonic operation. Other common choices of the p-norm are p equals 1, where we simply sum up the absolute values of the differences, so we minimize the mean absolute error, or the limit of p against infinity, which means we only take the vector element of delta which is largest. So it's the maximum operation, and that is called Chebyshev regression. So now we have defined what is the quantity that we want to minimize in order to train the parameters. So we have defined the loss function. Let us generalize this a bit. Most supervised learning machine learning algorithms can be formulated as the problem to minimize such a cost or a loss function. In general, we will call this function C, depending on the inputs x, the labels y. If it is supervised learning, we have labels y, and the parameters, which in general will be called theta. In our case of regression, instead of theta, we have used the vector w. In general, theta may not be just a vector, but may be a set of a whole bunch of things. So x and y are generally parameters. In our case of regression to a single dimensional target, y is actually just a vector. So the dimension L is 1 in our case, but it could be also multidimensional for multi-target regression. The pair x and y is the training data, and it consists of pairs xi and yi. As I said, here we call theta equals w for the case of regression, and because we have univariate regression, the y matrix just becomes a vector. We choose linear least squares regression, or first least squares regression. We haven't done the restriction to linear yet. And that means we choose the mean squared error as the loss function. As you see here, this is just the sum over the squares of the differences between predictions and labels. And we also divide over n, so we turn the squared error into a mean squared error because we want to normalize it by the size of the data set so that we always have errors of similar magnitude, independent of how large the data is or how many data points we have. Okay. So note that we can ignore the square root here, so we don't actually need to take the square root of c, because the square root of c and c have the same minimum, and this is what we are interested in. The learning problem then is to seek w, so to search the parameters that minimize the loss function. So we want to find the argmin of the loss function over w. Again, we can, whenever we write this, we can use or ignore the prefactor 1 over n because it does not change the argmin. It does not change where the minimum is. So we will do this however we please and however it's more convenient in the equations that are being used. Okay. This loss function has an interesting statistical interpretation. And that goes back to the derivation of Carl Friedrich Gauss, who introduced linear least squares regression. And the assumption of Gauss, which has the statistical interpretation, is the following. So we assume that the observations or the measurements yi that have been made are produced indeed by y hats, so by our optimum model. Of course, this is an assumption that relies on two things. First of all, we assume that we have enough data to actually find yi, and secondly, we also assume that the functions that we represent, the functions over which we search, can actually represent the exact function which has generated the data. This is something that in general we don't know. But so if these assumptions are valid, then we can do the following. We can say the measurement yi has been produced by y hat evaluated at the point where the measurement was made, xi, and the parameters w, plus a certain uncertainty. And this uncertainty, or a measurement error, is assumed to come from a normal distribution, so a Gaussian normal distribution. And here, for simplicity, we will just use a normal distribution with mean 0 and variance 1. This is in general a different variance, but for the sake of illustration, it is completely fine to work with a variance 1 here. So the random variable delta I is drawn from this probability density shown on the right here, which is the normalized version of e to the minus delta I square half. Now, the task is that we want to find W, which has the maximum likelihood of having produced this observation. So we want to maximize the likelihood of the data under this model. In other words, the probability that this model generates the observed data. And if we assume that individual measurements are statistically independent, so we often say they are IID, so they are independent and identically distributed. They come all from the same distribution shown here, this Gaussian distribution around y hat. Well, then we can simply take the product of the probabilities of generating every single point. And for that, we simply insert the measurement point into its respective probability density, and we take the product over all of them. So now we maximize the parameters of this function. We maximize W. Okay. So instead of maximizing W in this product, we can also maximize W in the logarithm of this product. Why do we do this? Because it is much more convenient to work with sums than with products. And the logarithm is again a monotonic function. So whether we maximize a function or we maximize the log of the function is irrelevant for finding the point where the maximum is attained. So we maximize the log of this product above, which means we maximize the sum of the logs of the individual terms. And the log simply cancels the exponential function here. So we are left with the maximum over the sum of squared differences, or the mean square error, plus or minus a constant. So there's this constant log of square root of 2 pi, which comes from taking the logarithm of the normalization constant in front of the product. But since this is just an additive constant, it again does not affect where the optimum is, and we can throw it away. Now there's a minus here. We can get rid of the minus by turning the maximization into a minimization. So this is equal to taking the minimum of the squared error. So we simply have the minimum squared error or the minimum mean squared error, which is again the same for finding the optimum. So this means that maximizing the likelihood under a Gaussian error model is equivalent to minimizing the mean squared error. That is the statistical interpretation. Now we get one step more concrete by saying what is the function that we want to fit. And now we restrict ourselves to linear least squares regression. So that means we assume that the function y hat is linear in the parameters w. And specifically, we write yw as the scalar product of the positions where the measurement was made, xi and w. That can be written out as a sum over the dimensions of x and w, as you see on the right. Now we can also write this in a matrix notation for all the data points at the same time. So the vector of predictions y hat equals the x matrix, which contains all the measurements in the rows and the dimensions in the columns, matrix product with the W vector. And that means we can write linear least squares regression by minimizing the 2 norm of the difference vector between the labels y and the predictions y hat or xw. So in general, linear least squares regression seems like a quite big restriction because we want to be able to represent nonlinear functions that have generated the data. But instead of trying to solve a nonlinear optimization problem, which is much harder, we instead linearize our problem by changing our original coordinates in which the measurements are made into features, and we do a linear regression in those features. And the feature functions which change the original coordinates, called Ri here, into the functions in which we then work, xi, these are called feature functions. So every data point is featurized by applying all the feature functions phi 1 through phi n. So that means our data matrix X has a size of the number of data points times the number of feature functions. And our linear regression model then has the following form. So y hat for every original data point Ri and the parameters w can be written as a sum over the products of the weights w1 through wn multiplied by the feature function phi 1 through phi n evaluated at the data point Ri. And this can, of course, be nonlinear in R. It can be very nonlinear. It only depends on how we choose our feature functions. So to give an example, if you choose the following feature functions, 1, r, and r square, and the corresponding weights, w1, 2, and 3, with that we can fit any quadratic function, f of r equals w1 plus w2r plus w3r squared. Now, given such a linear least squares regression problem, what is the optimal solution? We are choosing linear least squares regression for this lecture because it is so simple to solve. We do not need to iterate the solution or do gradient descent. We can just write it down in one shot using one linear algebra operation. All right, what is this solution? It can be shown, and I'm not showing this here, but this is a basic of linear algebra. It can be shown that the optimal solution to this minimization problem, minimum over y minus xw in the parameters w, is found exactly where it fulfills the normal equations. The normal equations are shown here. So this is one matrix vector equation, or an equation for every dimension, if you like. So on the left, you have a matrix, x transpose x, that's a matrix. It's a covariance matrix of the data x. This matrix multiplied with a vector w. And on the right, we have, again, a covariance, but this is a covariance vector of the data matrix x transposed and the label vector y. So the linear least squares regression problem has a unique solution exactly if x has maximum rank. So in other words, if the rank of x equals n, the number of features. Now, formally, we can solve the normal equations shown above using direct matrix inversion. So if you multiply with the inverse of x transposed x, then you get that w equals the Moore-Penrose pseudo-inverse. So this is the inverse of x transposed x multiplied x transposed y. And The interesting thing here is really the mathematical structure. So x transpose x is a covariance matrix, and x transpose y is also a covariance matrix. In this case, a vector, because we only look at one-dimensional regression or regression to one target. But if we do multi-target regression, this would also be a matrix with multiple columns. So then the solution for the parameter vector w can be written as the inverse of the covariance matrix x on x and the covariance matrix between x and y. However, this is a very unstable and inefficient way of finding w, so don't do this in practice. In practice, there are more robust and efficient ways of solving the normal equations, for example, using singular value decomposition. With this, we have introduced linear least squares regression. So we have introduced a machine learning problem on which we want to now work for a little while and analyze what statistical estimator theory is in this particular example. So now, in the next part, we will go into validation and hyperparameter selection. Specifically, we will ask the question, how should we choose our feature functions?